So, in the last lecture, or maybe last two lectures, we talked about multiplexers in detail and how to use them as building blocks or functional units in design of combination logic. Today we will see another circuit which is MSI, which is a decoder. So, first we will see what an encoder is and then a decoder, encoders and decoders. As the name suggests, one codes the various combinations into a smaller number of bits, the other expands it back. So, an encoder, for example, suppose I had 8 inputs, 8 to 3 encoder. Assuming only one of the inputs is active, could be active high or active low, at a given time, we will know, all we have to know is which of these 8 inputs is active. So, you need only 3 bits for that. By combination of these 3 bits, we can determine which is the active input, all others are inactive at that given time. So, this is the process of encoding. Encoding reduces the possibilities, the number of inputs required from 8 to 3, for example, or 16 to 4. So, compressing the data from different possibilities into a smaller number of bits. That is the process of encoding. So, in this case, we will have 8 inputs. Let us call this I0, I1 and I2, etc., I7, and we will have 3 outputs. We will call them O0, O1, O2. This is MSB, this is LSB. So, assuming, of course, there is a problem in more than one input can be high at the same time, then what happens? In which case we talk of priority. If more than one inputs are active at a given time, then the output will be, we do not know how to determine the output, but there can be some rules. You can build some rules into that. We will not talk about that. I am just going to talk. I am just going to tell you about this type of MSI which are available. So, for example, if I5 is high and all other inputs are low, the output would be 101, right? So, this process is called encoding. Now, the question is, as I said, if more than one input is high, what will happen to the output? We can say, we can have a scheme of, we can have a procedure or a rule for this. One scheme is called the priority encoding. I can say the input the input with the highest binary value would be recognized, or the input with the lowest binary value recognized. So, you can say priority goes from I0 to I7. That means, if I0 and I1 are both active, I0 will be coded, I1 will be ignored. It's one scheme. That's all. The rule is, you make the rule and then build a circuit accordingly. Or I can say lowest order. I can say higher inputs have priority. That means I7, supposing I5 and I6. If along with I5, I6 also is active high, I can say I6 should be recognized and not I5. Fine. Then the output will not be 101, it will be 110. Anyway, this is called the encoding process of reducing the number of bits into a smaller number of bits without any loss of data. The reverse of this, the complementary of the complementary IC, the complementary operation is called the decoding operation. So, this is an encoder, 8 to 3 encoder. So, we will have a 3 to 8 decoder. So, I can put this here straight away, 3 to 8 decoder. 3 possibilities. Out of them, one of them will be, no, now there is not a one of them, because any combination of this can happen, because there will be 8 different outputs, corresponding output will be high and all others will be low. So, I can have again I0, I1, I2, lowest order to highest order bits, and then I can have here O0, O1, O2, O7. Now this 101 goes here is 101, making O5 high, all others low. This is a decoding operation. This is an encoding operation, this is a decoding operation. Why do we need this? I have 8 possibilities at the input and 8 possibilities are required at the output, and I don't want to run 8 lines from input to output, because one of these lines will be active high all the time, I mean at any given time, and others will not be. So instead of running 8 lines and finding out which is active high, I can send 3 lines with a coded information into that, and then at the output will decode it, at the receiving end will decode the 3 bits to find out which input exactly was high here at the sending side. This is compression data. Data is compressed. 8 lines instead of running because of the length requirement. We can do it with 3 bits. 3 lines will do the job. And if there is a priority scheme here, it doesn't really affect this here, because here it is an expansion scheme. So 3 is expanded into 8. So whatever is the combination will be expanded accordingly. Here of course there may be a problem with more than one inputs being high. In that case we will have a priority scheme built in. So in such a case it will be called a priority encoder. Normal encoder or a priority encoder. A priority encoder will have a priority scheme built in, saying when more than one inputs are high, which of those inputs will be recognized and coded at the output. Now how is going to help us in our combination logic design? Just as multiplexers helped us to design combination logic without going through the gate design, because after all inside you can build these gates. You can draw a truth table, can you not? Can you not make a truth table out of this? A, B, C are the 3 inputs, or I0, I1, I2 are 3 inputs, O0 to O7 are 8 outputs. I can draw a truth table. 0, 0, 0 combination will make O0 high, all others low. So each of these will be, so I can have a gate realization for this. Likewise I can have gate realization for this. All are gates finally. Basically they are all AND OR inverter. I told you long ago, AND OR invert is the sort of a universal combination by which any circuit can be recognized, can be designed. Same thing applies to the encoder or decoder. Or we don't want AND OR combination, you can have an AND gate, universal gates, or any other combination of gates that you want to work with. So what is the advantage of using this? So now we have this scheme of so many gates, the gate function, equivalent gate function, about 10 to 15, 20, I don't know, depending on the number of inputs, number of outputs, and priority scheme is built or not. Somewhere between 10 to 30, 10 to 20, 10 to 30 gates will be there. So when you compress it and make it as a single IC and make it available to you in putting in a one IC chip, then it becomes a medium scale integrated circuit, MSI. Our aim in this last few lectures has been to use these medium scale integrated circuit components in the design of combination circuits. So we have to see how this hardware encoder and decoder will be used in combination logic design. So let us say design a combination logic using encoder, decoder. Combination logic design. This is a very straightforward procedure here, because it is not even in multiplexer, of course it is mapping procedure was very clear, but not even that here. It is a straightforward case, because when you have 3 inputs and 8 possibilities, this is similar to the truth table, isn't it? So that means all possible minterms are generated. The question is, one of them will be high, all others are low. But in general though, when you have 3 inputs and 8 outputs, it is equivalent to a truth table with 3 inputs and 8 outputs, 3 inputs, 8 outputs, each of these outputs being a min term. and if you know which are the minterms which are high for that particular combination of the hardware, then I can combine them all together and make a circuit out of it. It's as simple as that. Suppose I want to realize a function f sigma f of a b c, a being MSB and C being, you have to be always very clear when you say all these things, which is MSB, which is LSB. Here I am considering this as the MSB, this is LSB. So when you map it, I should connect A to this, B to this, C to this. That's why I am writing in this fashion. F of A, B, C will be equal to sigma, let us say, arbitrary, whatever you want, 1, 0, 1, 4, or shall we use the full adder? Tell me, what are the 1, 2, 4 and 7? Is it the sum of the full adder? Is that right or not? We have seen full adder so many times, 1 bit full adder. Minterms which are high for the full adder, sums are minterms 1, 2, 4, 7. So we will realize a full adder using a. That's what we did with multiplexer to start with. We will do the same thing with decoder. So all I have to do is to get my 3 inputs. This is C in. Here this will be A, this will be B, this will be C in. That order I am writing, so the same order should be mapped. And output will be M minterms. This I will call this I0, I will call this M0, which is same as I0. I will not, don't get confused. This is I's which are equivalent to the minterm, so I will put I0 inside and M's outside. This is M0, this is M1, etc. This is M7. Now in order to get a full adder, I need to combine M1, M2, M4, M7 into a OR gate. Correct? So I take M1, M2, M4, M7, this is my F, which is the sum of the full adder. The simple scheme of realizing a combination logic using a decoder, 3 to 8 decoder. This is a 3 to 8. Is it the only function I can realize? If I have one more function using the same minterms, I can also get it. Suppose I want to carry also in this, can I use it? Can I use the same decoder for this? Of course I can. So my carry would be, I will call this F1 or F sum, F carry out of A, B, C in, or if I remember correct, it was 3, 5, 6, 7 sigma is that right? These are the minterms for which the output is 1 for the carry. So I can combine them. This is now required, this requires now M3, M5, M6, M7. So M3 would be here, I3, M5, I6, M3, M5, M6, M7. So we'll have to take M3, M5, M6 and M7, put it in OR gate, and this is my F carry out, F sum. So 1 3 to 8 decoder and 2 gates, I am able to realize a full adder. That is the MSI concept, medium scale integrated circuit, replacing the bunch of gates. May not be the most efficient way, as I said. It's a mapping process. In the mapping process, two possible problems. One is that the mapping itself may not be efficient because the hardware availability is limited, and you have to get the best possible way of doing it. Second thing is, the second limitation is that there is not always there will be a straight cut method for doing it. As I said the other day, it's a heuristic method, sort of an intuitive method. You have to identify the hardware availability and the input requirements and try to match it. So there may be an error in that. Even if you do a software for this, software may not always do it the optimum way. So we may use some extra hardware in that process because of that, or there may also be extra hardware required because there is no one-to-one correspondence for everything that I want to realize. I may not have an equivalent MSI. But still it is worth it because the number of gates gets drastically reduced in terms of number of ICs gets drastically reduced, saving space, whatever, power, cost, size. The same repeated parameters we have been stressing on right from the beginning in this course. Of course, I am giving you a bare bone sort of approach to the problem. There are some practical issues here. It's a conceptual, we are building most of the things conceptually. We are not getting into circuit details, of course. As I said, that's not required. If you are going to use a logic designer, you know what is the input-output specification. But even a logic designer should know a few things. For example, you should know how much voltage you should apply. Should you apply 250 volts or 10 kV or 5 volts, 3.3 volts? Of course, you will get it from the data sheet, but you should know, look at what order of voltage you are looking at. What is the current levels? What type of, suppose you buy an LED to show your, indicate your output, what type of LED, what type of current is available, whether an LED can go with that. These are things you should know, of course. A little bit of the gate level electrical specification, we will call them. Even though it's all logical and we are not getting to the physical, the next is called physical design, where you replace this logic by components which are available. We are not getting into that because of the background being not adequate in terms of the electronics. But there are certain things. One of the things is there is always an enable class in all of these things, whether it's a decoder, an encoder, or a multiplexer. There will always be a signal called enable signal. I will introduce it here because it is all same in many ICs, but I thought sometime I should tell all these things to you before you get out of this course. Like this preset and clear are extra signals in flip-flops. For a logical design or a simple analysis, understanding of the flip-flop, you don't need to know it, but then I introduce it. Likewise, here I want to introduce a signal called the enable signal. Enable usually is a negative signal. I mean, it's active high, active low. That whenever you put a bubble on a signal, it means the signal is active when it is low. When it is high, it is not active. Whenever you don't put a bubble, signal is active when it is high and not active when it is low. Okay, that's an enable signal here. And this has to be tied to ground if this circuit will work. This is the way they represent ground in electronic circuits, or this is 0 volts really. That means if enable is low, whatever we said about this decoder encoder is true. If enable is high, if I do not connect properly enable to ground, then whatever you give here will not reflect in the output. Output will not behave as expected in the truth table. This is true of many ICs. Multiplexer has an enable signal. Encoders have enable signals. Decoders have enable signals. Sometimes more than one enable signals. These are signals that are required for controlling. I may have this circuit on a board, on a system. I may have this IC on a circuit, but I may not want that to be active at a given time. I want it to be active at some other time. So how do I control that? I cannot just pull it out whenever I want to put it in, and whenever I do not want to pull it out. It's not possible to physically remove a IC and put it back. Suppose you want the IC not to affect the rest of the operation. You don't want the IC there at that time. You have to pull it out, and you want it there, you put it in. But it's equivalent to electrical equivalence of removing and putting it back. When enable is low, it is equivalent to putting it there, keeping it there, and when enable is high, it is equivalent to removing it so that it is not there. So electrically it is not there. Physically it may have inserted, you may have inserted the IC in a socket, but electrically it is not there. Electrically you can ignore it. Such things are required very much because many designs are complex designs where several ICs have to coexist and certain operations require certain paths. At that time the other circuit should not come in the way. How do you control it? By these things. And there may be more than one enable. An enable, usually when you say enable, if you want to be very clear, if you don't know all this, since you don't have the circuit diagram, so every time you are talking about a decoder, you cannot draw a circuit and show enable as a bubble. So what you say is simply say enable bar. So people understand. When you say circuit as an enable bar, which means I should make it 0 for it to be normally active. The normal operation. So enable 0 is normal operation. And enable 1 is what? Abnormal operation or what? What do you write there? Huh? Electrically not there. It's an electrical open circuit. I have to define a term here. Since I have not defined the term, I am not able to write it. It's called tri-state operation. Output tri-states. I will tell you what it is right now. I have to introduce again. These are some compulsions as you go, and I have to introduce a new term. I can't keep postponing these things. Output is tri-stated. What is a tri-stated? We will see. The same as electrically not being output, or I can say output impedance is very high. Output high impedance. If you don't like this term now, since I have not explained that to you, I'll do it in a minute. Output impedance high. Output high impedance state. High impedance means it is impedance such that it is as high that you can ignore it. You know, all of you have gone through electric magnetic circuits course, so you know what it is. A high impedance means physically. When you put, let us say, 100 megaohms, it's as if it is equivalent to open circuit, right? Practical reasons, of course. Mathematicians may argue that it's not 0, it's not open, but we are engineers, not mathematicians. So we have to be practical. When you do something, you have to tell the practical implications. So high impedance means the output is as if it is disconnected from the rest of the circuit. Like you sit in the class and disconnect yourself from what is happening, you know. Think about something else. That's exactly what high impedance state is. You are physically present, mentally off. Many times it happens, right? I do it. When I go to some meetings, which is boring, but I have to be there because I'm required to be there. It happens to everybody. Only then I wish that it doesn't, I hope that it doesn't happen too often in this course, right? That is exactly high impedance. So we have a gate function called tri-state gate function, which is what will be put in output for these operations. So we will come to that, but there can be more than one enable. So this is only one enable. In a practical decoder, like 3 to 8 decoder, generally there are 3 enables: G1, G2A, G2B. G2A and G2B are active low, G1 is active high. So if this circuit works normally, this is a practical 3 to 8 decoder. Actually I can give you the IC number if you want to. It is 74138. Doesn't matter. Don't have to remember numbers. I don't remember numbers. You can always look up the data. In fact, I'm not even sure if it's 128 or 138. I think it is 138. If somebody has a book, you can have a quick look at it. Anyway, now this particular IC, which is 3 inputs, 8 outputs, has 3 enables. That means for the circuit normal operation, G1 should be high, G2A and G2B should be low. only then the circuit will normal operation. Why do you need 3? As I said, sometimes the control signals, I want to control it, I may have to control it from different points of view, from different ways. So I can use these 3 combinations. Only when all the 3 occur as required, only then the normal operation. Rest of the time, otherwise, outputs are tri-stated. Otherwise, outputs are high impedance state. Outputs are in Z state. I will write now. Instead of writing every time high impedance state, capital Z they put and say Z state. Z state means high impedance state. For digital circuits, this is a accepted nomenclature. When you say Z state, it means it's high impedance state. Accepted nomenclature for digital. One other practical note on this IC, practical IC. I wish I remembered whether it's 128 or 138, but it's okay. Let us assume 138 for now. Please check up, maybe 128. Forgot to look up before coming. Right. The outputs are not active high. Output are active low. So instead of getting O0, O1, O2, how many? 1, 2, 3, 4, 5, 6, 7. I don't have time, space here. I will probably put the enables here, doesn't matter. Enable does not have to be bottom because it's all not what is the way. It's only a representation of circuitry in the book. You can write it here also. G1, G2A, G2B. This is I0, I1, I2. This is LSB, MSB. O2, O3, O4, O5, O6, O7, and these are active low outputs as well. That means if a particular combination occurs after enable is properly connected, of course. So assuming this is 1, this is 0, this is 0, I have properly connected the enables. If this is the only circuit in my only IC and it's not being required to be controlled by any other external, any other event in the circuitry, I can directly connect it to ground and power supply. These are control signal does not mean that it will always be controlled. Whenever we need to control, they are available to you. If you do not want to control, you want a permanently this normal operation, always, then there is no problem. You make 1, 0, 0. Connect it to high, connect it to low, connect it to low of the power supply, it will work always, normally. So that is possible. It's not an excluded operation. Now, when we having done that, suppose I give 101 again or 110. O6 should be active high, all of that should be active low. But because we have bars on the outputs, if you want to even put a bubble on the outputs, bar and bubble are redundant. Bubble is only when you draw, whereas when you are writing, when you are looking at the data sheet, you will see these signals I0, I1, I2, O0, O1, O2, so you need a bar for that. So O6 will be low and all others will be high. Normally it will be other way. When I say active high outputs, O6 should be high, all others should be low. In this case, this is a practical decoder. It is available. 3 enables, 3 inputs, 8 outputs, or active low. So if I want to now use this practical decoder in my adder circuit, can I do that? Because I have connected these 4 into OR gate to get sum, connected these into another OR gate to get carry, assuming these were active high, but now I learned from the data sheet that it is not active high, these outputs, they are active low. So now active low outputs, how do you change this design? NAND gate. I use NAND gates because when you put, see what we want is M1, sum is M1 M2, M4, M7, but what is available is only M1 bar, M2 bar, M6 bar and M7 bar. So S bar, we'll see what is S bar is. So S bar would be M1 bar, M2 bar, M4 bar, M7 bar. But we want inverse of that, we want sum. So sum is NAND. It's NAND. So connect this what? 1, 2, 4 and 7 into a NAND gate, we get sum of a full adder. If I connect my A, B and C in as a full adder as inputs. Likewise, I can connect this through a NAND gate, M3, M4, M3, M5, M6, M7, another NAND gate, M3, M5, M6. Carry out. Carry output is M3, M5, M6. So some of these practical things you should know. That's why I thought I will introduce this. When you look at a circuit, logically you may be right, conceptually you may be right, but then it will not work because you are assuming the outputs will be active high, but they are really active low. Or you did not know there was an enable which has not been properly connected. Or you did not give the proper power supply voltage and ground. You should know which pin has to be given power supply, which pin has to be given ground. So all these things you should know. Of course, you can look through the data sheet, but you should know there are a few things to look for, Data sheet you don't have to remember the details, but you should know to look for something. Without knowing that there is something to look for, how will you look for them? That is why you need to know these things. Coming back to the tri-stating, what do you mean by tri-stating and how is the active high? Suddenly we say the active, because we only know two things. A circuit can be an input or output can be low or high. Low means 0, high means 1 for positive logic, 0 volts and 5 volts, 0 volts and 3.3 volts, 0 and 1.2 volts, whatever. But now suddenly I am introducing a third concept called the output can be 0 or 1 or a high impedance state. So what is the high impedance state? So these are called tri-state gate. The tri-state meaning there are three states, tri-state gates. Inputs, the gate tri-state has three states, low state, signals of tri-state gates has three states, low, high and high impedance. So this is 0, this is 1, this is C. This third state, that's why it's called a tri-state. Actually, this tri-state is sort of a long ago coined by National Semiconductors, major semiconductor manufacturers, and they patented it. And the term was patented. So other companies could not use this tri-state. They had to say three-state buffers. I think now it must be sufficiently long to patent must have expired, so they can use it. So you will find in textbooks freely tri-state, whereas when you look at company literature and some other company other than National, they will always be careful to write three-state buffers, because somebody can go to court on patent violation. Tri-state is as if the tri-state was, because the word was coined by National Semiconductor. That was long ago though. It's history now. Anyway, so what do you mean by this? So I have an input and output. Let us take a simple inverter. Input is A, output is A bar. So this is two-state gate. V is 0, A bar is 1. So we know the truth table of this inverter. f, f is equal to a bar. All of us know this. Now we are introducing a third concept. Output can be either 1, 0 or z. How do you know or how do you control this? When you want output to be high impedance, how do you make it high impedance? So I need some other extra input for that. So I have a third input called enable input. That is where the enable concept came. So if enable, this is true if enable is 0. So now this truth table becomes true or normal operation only when enable is 0. If enable is 1, which is high, as I said, enable is usually an active high. It is not a rule. You may find a circuit which is enable high, so don't always assume. Look at the data sheet always. Before you use an IC practically, you have to look at the data sheet. Today everything is available in the web. You can go to the website of that particular manufacturer, search that IC you are looking for. That fellow will give you the data sheet input. There will be so much data, it will confuse you. You will have to look for what you want. On the other hand, if enable is low, enable is high, is disenabled or disabled. Enable is opposite of enable is disabled. Now, if A is 0 or 1, output is high impedance. Doesn't matter what the input is, output is always high state. Now, this is a very important thing, development in the digital hardware development. Conceptually, there is nothing here, but hardware wise, there is a feature, the third feature. Now, if I put all these inverters or any other gates, this is only inverter I gave an example. The same thing can apply to any gate. You can have an AND gate with an enable, in principle, of course, may or may not be there as a component. So if the enable is low, AND gate works as AND gate. Enable is high, whatever inputs you give the AND gate does not give you the AND output, it gives you a high impedance output. That is what I said just now in decoder. It can also be there in encoder, it can be in multiplexer, it can be anywhere. What is the idea? Now when all these ICs are present, like that, some other gate, and I am connecting them all to a destination. These are different sources of data or control functions or whatever, and this now will go to another circuit here. I want this combination, but at one time there will only be one source of data. So when at a given time I would like the output here should be determined this gate only, and this should not interfere. That means this output will be inverse of this, and this should be this. At some other time I want this output should be inverse of this, which should be this. So I may have different sources of data or different connections in my circuit, all feeding to a same input of a same gate, and I want only one of those inputs to be effective at that time, so that the output will be determined accordingly in my process, in my behavior, in the circuit description. So what is the point? I can do it, and when I don't want it, I can remove these ICs. As I said, that's not a good solution, not a practical solution. If I don't do that, what will happen is, even though this is, if it is high or low, all of them have to be high or low. If this is high and all of them are low, low is 0 volts, that means practically ground. So I am trying to push this high voltage into this, at that time this is low and then this gets grounded. This also gets grounded. So whenever I am trying to pull this up using the output of this, because it is high, these two gates will pull it down to 0. Right? These are the problems. So now if I have that Z feature built into all of this, all are tri-states gates. Now all these gates are tri-state gates. I don't think National Semiconductor is going to sue me, so I'm going to use it tri-state. Then I don't have no problem. So I will control the circuit such that when the output of this has to be the input of this, I will make sure these two outputs are high impedance, which have no effect practically on the operation of this circuit. When I want this output to be the input of this circuit, I will control these two outputs to be high impedance so that these two circuits will not have any effect on the output of that circuit, which means electrically you are disconnecting it, physically you are not. So this is also built in many circuits. Enable inputs are a very common feature in multiplexers, all ICs, especially MSI, LSIs, because these MSI and LSI will sit on a what is called a bus. This is called a bus. A bus is what? What is a bus? Real bus. What is a bus? It transports a lot of things at the same time, right? Many people can join the bus and then go. Many signals can join and go. So the common bus is there. All these outputs feed into a common bus. But the input will be used, only one of those common signals is useful to the input. So I have to disconnect the other inputs from the bus. Physically disconnecting is not possible, so I electrically disconnect the other inputs which are not required at a given time. So when you have a bus operation of these ICs, especially MSIs and LSIs, as you go complex, more and more complex in design, you will use all of these in your design because very complex and all of them coexist. At the same time, only a few of those will have functions at a given time, roles. Rest of them will be something like asking somebody to shut up. A lot of people are there, only one person is allowed to talk. Something similar to that here happens. So now we have practically covered a lot of grounds in the case of MSI, LSI, the basic concept of MSI based design as against gate based design. The couple of the advantage is that there is a simple hardware which can replace the tons of gates with all the attendant advantages in terms of the cost, size, power consumption, everything, speed of operation, performance. A couple of problems, the best possible match may not be possible, best match may not be possible either because of the non-availability of the hardware feature or because of the limitation of the design procedure, but still it is worth it, much better than the other solutions. Then we talked about mux and decoder, which are two major components in MSI in design of these things, and we talked about how to map given hardware, given corner map into this hardware. We talked about enable feature and how to put active low and active high outputs are possible, and we have talked about enable feature and how enable features control the operation. What happens when the circuit is disabled? It goes into high impedance state, or high Z state, and this is the idea behind that. The next step we will take is towards LSIs, large scale integrated circuits, and they have to be programmable, as I said, because when you have larger and larger circuits, it should be useful more and more. I cannot make a simple circuit which is mappable or not mappable, so I just throw it and get another circuit. When I make a large scale integrated circuit, it should be available for many operations, so they become programmable. We will talk about it, but before that I want to mention that MSI is not restricted to only combination logic circuits. These are combination logic building blocks, multiplexers and decoders. But if you think of a counter, a 4-bit full adder is a MSI, right? If I can make one 4-bit full adder, one IC, each full adder you know about what? About how many gates? There's 2 exclusive OR gates for add, and 4 gates for the carry and all that. So and if you add this, what will happen now? 6, something like 24, 25 gates. It qualifies for an MSI. So functionally, there can be same things a small scale integrated circuit can do, but then put them together becomes an MSI. The same way, a counter can be, a register can be a MSI. Even though a flip-flop will be a small scale integrated circuit because it only has a couple of gates or at the most 4 or 5 gates, including clock. When you put flip-flops together to make a register, 4-bit register, a 4-bit counter, they become MSIs. So we have now used MSIs without our knowledge. 4-bit full adders we use in our design. 4-bit full adders and adder, subtractor and all that type of thing. We are talking about counters and registers, shift registers. These are all MSI circuits. They are also MSI based design. Of course, you can also use them in some other ways. We will see it later on. First, let me finish the programmable aspect of combination logics. Large scale integrated circuit with programmable devices called PLDs. PLD stands for programmable logic device. So next lecture we will start talking about PLDs, programmable logic device. But later on we will come back to revisit the MSI sequential circuits, how they can be used in roles which we are not familiar with. Now we know how to use it as a counter register, but you can also use it for implementing the sequential logic. We will see that later.